Okay, hello everyone. This is the video notes for section 5.1. It shouldn't be that long because it's not a very long section. So it's called Eigenvalues and Eigenvectors. I really would advise you to read over the section first, even if you don't understand what you're reading, to read over the section first and then go over the video notes. It'll just make more sense because I don't. This is a short video and I'm trying to keep it short. I don't cover everything that's in the section, so you need to make sure that all the other things that I don't cover that you get from reading the book. Okay. So eigenvalues and eigenvectors. And so here's the definition. And so again, this is something you should be writing on your note cards. So let A be an n by n matrix. And lambda, that's the lowercase Greek letter lambda, is an eigenvalue of A if there exists a non-zero vector x such that A times x equals lambda times x. And so x, the vector x, is called an eigenvector of A. Okay, so make sure you understand that definition very carefully. All right, so let's look at an example. And so given we have this 2 by 2 matrix here and this vector x here, given that A is that matrix, show that that is an eigenvector. So it's not asking you, is it? It's saying show that it is an eigenvector. And again, by definition, that means that A times x equals lambda, which is some scalar, lambda times x. Okay? And so what we do is we take A times x, so we multiply our matrix times our vector, and we all know how to do that. And so we end up with the answer 6, 3, and we can see that there's a common factor of 3 in both those terms, in both those entries. So we can factor out a 3, and we're left with 2, 1, which is our x, right? So that tells us that 3 is an eigenvalue. So lambda equals 3 is an eigenvalue for the eigenvector 2, 1. Okay, it's pretty straightforward, right? Not bad. All right, let's look at finding eigenvalues and eigenvectors. So again, by definition, we have this right here for an eigenvector where x is a non-zero vector. And so if we subtract both sides, it's always easier to work with 0 on the right, the 0 vector on the right-hand side. And this is with equations in algebra or pre-calculus. It's always easier if you're solving to set your equation equal to 0 when possible, right? And so it's the same applies when we're talking about matrices and things of that nature. So we subtract lambda x on both sides, and then we can factor out the vector x. And so we have A minus lambda I times x equals the 0 vector. Now, A minus lambda I, and again, I refers to the identity matrix. Okay, so depending upon what square matrix we're talking about, it refers to that particular identity matrix. So I could, if I want to say I sub n, depending upon what matrix you're in. And A minus lambda I must have a non-trivial solution. And why is that? Well, by definition, x has to be a non-zero vector, right? And so since x has to be a non-zero vector, then to solve this system, it has to have a non-trivial solution, right? Because otherwise, if it had a trivial solution, remember the trivial solution means that all the entries, all the scalars, all the weights have to equal 0. That's the trivial solution, which would make x a 0 vector, but by definition, it's a non-zero vector. So that's why A minus lambda I must have a non-trivial solution in order to make this true. Okay, and the set of all those solutions, we call that the eigenspace. So we have eigenvalue, eigenvector, and eigenspace. Okay, and so for a 2 by 2 matrix, A minus lambda I, and this is just in general, this is how that would look. It would be the entries, as you see along the diagonal, have a lambda, and then the other B and C just stays there. Okay. All right. So now we're given again, let's look at this 2 by 2 matrix with lambda equaling 4. Find a basis for the eigenspace corresponding to lambda. Okay, and so since lambda is 4, this is the equation that we need to solve for to find the eigenspace. And so the first thing you do in approaching this to find the basis for the eigenspace is first you find a minus lambda I. Okay, and so in this case our lambda is 4, so a minus 4I, once we do the math on that, and you all know how to do this, you end up with the matrix -1, 2, 3, -6. Okay. Then step 2, so that's step 1. Step 2 is put it in our REF to find the solutions. And again, since we're talking about non-trivial solutions, we're talking about free variables, right? Because a trivial solution, remember, in terms of our systems, going back to chapter 1, if we have a solution, it's either unique or infinite. And if it's infinite, that means we have non-trivial solutions or free variables. Okay, and so we row reduce here. And again, anytime throughout the video, you can stop and try it on your own before you look to see how I did it. And then we have a pivot column there, and we have our free variable here. And so our x vector, which is x1, x2, those are our weights, equals 2 times x2. That's what x1 is, and then x2 is just x2, or if you want to call it a, you know how we change it, you can do that as well. And so it equals x2 times the vector 2, 1, and so there's our eigenspace, right? And this is something to note. When you're talking about bases, the notation for a basis, you don't have to put, so notice I didn't put the span of 2, 1. Now, if you put that, that's fine. I won't mark it off, because if it helps you to make sure when you're talking about column and the null space to put span, that's fine. But just know whenever you're talking about a basis, the span is implied, right? Because for a basis, it's implied 2 things, right? If this is truly a basis. 1, that the vectors are linearly independent, and 2, that it spans that space. So you don't have to put span. So you don't have to put span on the outside of there when you're talking about basis, okay? And so again, if you just want to be consistent and put it there, I'm not going to mark you off, but just know whenever you're referring to the basis, it's implied that it's the span of that vector or those vectors, okay? So just wanted to mention that, because the book, they put the span, they don't use span when they're talking about basis, but they do when they're talking about the column vectors on the null space, or they use the linear combination, okay? All right. A nice theorem we have is that the eigenvalues of a triangular matrix are the entries along the main diagonal, okay? And so, for example, if we looked at a 3 by 3 matrix, this is upward triangular. If we look at this and we take a minus lambda I, then this is the matrix we receive, and so we need a minus lambda I times x equal to 0 vector to have non-trivial solutions, i.e. free variables. And so this only happens when one of the diagonals equals 0. And I want you to think about that. I'm not going to answer it here, but I want you to think about, why does that have to be the case? Why does it have to be the case that we'll only have non-trivial solutions or free variables when one of the diagonals equals 0? So think about if none of these equaled 0. What would that imply? Okay, and I'm going to leave that there. All right, so since that's the case, then that means since it only happens when one of the diagonals equals 0, that means that we set each of these diagonals equal to 0. And so those become our eigenvalues, okay? So again, go back over it. There's some other things. If this isn't making sense, go back over in the book and read over, because they give more information on this. And this is the last thing that we're going to do. So like I said, this is a pretty quick video section. Although, again, go read the section in the book, because there are some things I'm purposefully not including so you can go read the book and you're going to be responsible for it. So make sure you go read the section. Okay, so eigenvectors form a linear independent set. All right, so if we have, the theorem says if V1, V2 up into VR are eigenvectors corresponding to distinct eigenvalues lambda 1, 2 up into R, then V1 through VR are linearly independent. And I forgot to put a LY, so make a LY in your notes for linearly independent. Okay, and so here we have an example here that, so A is this matrix, and it's upper triangular again. And so the eigenvalues are the ones along the diagonal, 3, 0, 2. And so 0 is an eigenvalue if and only if ax equals 0x has a non-trivial solution. And again, you might want to just stop and think about, well, why does that have to be the case? Okay. And here's just another example. So if we had, again, this is lower triangular matrix. So eigenvalues are 4, 1, and 4 if we look along the diagonal. But this is just something to, in terms of notation, we only write 1, 4 with multiplicity 2 since it appears twice. So we don't have to write 4 twice. We just say 4 has a multiplicity of 2. Okay, so this is the end of the video. Again, go over and read section 5.1, and on Monday you'll have a worksheet to work on problems similar to this. All right, bye.